That's Jason Lee. He's developing the mobile and the signal processing, the speech processing. I'm working on the MSP430 microcontroller and connecting all these devices. So when I first started researching this, it was staggering to see how many people had some degree of hearing loss. 17 million Americans. Many of those people rely on hearing-assisted devices just to get through their daily lives. The most common hearing-assisted device is the hearing aid. It's ubiquitous when we think about hearing problems and hearing impairment. So recently, there's been an absolute explosion in the mobile computing market. So there's been a convergence between the two, which is inevitable. A good example of this convergence between mobile computing and hearing assistance is the Bluetooth streamer. A Bluetooth streamer is a device that the user wears around your neck. It uses Bluetooth to connect to the mobile phone, and it uses the hands-free profile. So just like a normal Bluetooth headset that people that don't have hearing problems can use, it extends that using an FM transmitter. It transmits to an FM receiver that's found in a newer model hearing unit. So it's very low power, and it allows the user to use their phone without having to take them out. So it's a good system. Our contribution to the system is to add an audio memory. So we're going to add new applications using memory built into the device that the user wears. Not leveraging the capabilities of the phone, we're going to use the device itself. So our first application is a hearing aid orientation. When a user gets hearing aids for the first time, they don't really know how to use the system yet. It's got a learning curve. To be able to distinguish, hard to distinguish sound, it takes practice. So to facilitate that, we play sounds to the user that are hard to distinguish, and we provide them immediate feedback. With repeating this testing paradigm, we think we can make the system help the user orient to their hearing aids faster. Our second application is the personal audio recorder. When we describe this, we describe it as like TiVo for your hearing. So there's a continuous audio recording loop going on in the background on the device. And when the user needs assistance, they can indicate to the device by pressing a button they need assistance, and then they forward that information will be forwarded to the mobile phone, where we can do additional processing to extract information that's useful to the user. So our progress so far is we've built our circuits, and they're in testing now. We have the MSP430. It is acquiring audio and playing it back. We have integrated it with an Apple iPhone for control of that system, and we have a prototype of our speech recognition on a PC. And our next step is to integrate the full system and do some clinical testing. We're also working with Dr. Torlot, thank you, and Dr. Thibodeau at the Collier Center. So we'll be working with her to do some clinical testing. Thank you. Questions? Sir?
So this device works with hearing aids or independent of hearing aids?
With hearing aids.
With hearing aids, okay.
Yes.
Like the TiVo for the hearing.
That's
I
how
love
the
that.
idea came out.
Yeah.
TiVo for the years.
I could use that today. settings on how you're going to evaluate this for human subjects?
That's mainly for the orientation paradigm, so we can get their feedback and see if they improve.
Any other questions?
Yeah, I would come up with a qualification document of some sort. You know exactly what you have to do to succeed.
Okay.
I mean, saying, hey, I hope you like it. You'll fail, I mean, usually.
Okay.
So tell them exactly what you got to do to succeed next semester.
Thank you very much. Next presentation is the ultrasound condition.
Hello, my name is Nick and I'm here today to talk to you about our ultrasound positioning system. Standing to the right of me are my colleagues, Matthew Brennan, our main signal theorist, Chris Baroni, our main programmer, Peter DeBerry, our main circuit designer. I myself assisted Chris mainly with the programming this semester and also set up a mock visual interface for our positioning system when we expanded to 3 dimensions. Our main motivation in creating this system was to design something similar to the local positioning system, but a system that operated locally, so within a range of about 1 meter, and accurately, so with an accuracy of about 1 millimeter or so. Unfortunately, electromagnetic waves used in the local positioning system travel too quickly to accurately sample with inexpensive clocks. So we instead decided to use ultrasound waves, which travel much more slowly, around 900,000 times more slowly, and are much more realistic to capture and sample within our budget range. Our ideal goal for the semester was a high accuracy system with fast update rates, low power consumption, and a relatively low cost. So our focus for this semester was to develop a proof of concept. We set up a circuit that was 2 transducers, a receiver and a transmitter, and we tried to gauge the distance between them and see how accurate we could get at what kind of metrics we could establish. And we were quite successful. We managed to, our results were essentially a maximum error of 2.7% and an average error of less than 1%. That was about a week ago. We've actually significantly improved those figures since then and are getting an average error of around 0.5%, it looks like right now. We had some challenges while designing the circuit, namely device characteristics. We had some problems with op amps. We had some weird wire crosstalk issues while designing the circuit, which were amusing to deal with. And we had some transducer resonance issues that really put a stall in sort of our progress for a while. Next semester, looking forward, we'd like to deal with those transducer resonance issues. A best case scenario would be to get a 1-to-1 correspondence between the signal we transmit and the signal we receive. But even if we don't achieve that, we'd still like to reduce the amount of time the receiver circuit spends oscillating. That way we could have faster update rates, essentially. Next, we'd like to develop a signal encoding and correlation link that gave us a more accurate timestamp of the receiver, so we'd be able to more accurately calculate a distance. And lastly, we'd like to expand to 3 dimensions to make it essentially a position tracking system. Right now, we've got the basic concept established, but we haven't yet sort of layered on the extra dimensions that will make it sort of a viable product. So we'd like to thank you for listening to this presentation. I'd like to open the floor to any questions.
Within a 1 meter positioning?
Yes.
What kind of application would you do?
Oh, yes, my apologies. So industrial processes, things like CNC machines, any sort of robotic vision, a wide variety of commercial applications. We eventually want to set it up so that it can output any of the measurements it makes to a computer, and we can track in real time, like somebody moving the transmitter through any sort of free space within that distance.
You said that you would like to expand to 3D, but are you currently 1-dimensional or 2-dimensional?
It is currently 1-dimensional, but the concepts we have, our transceivers have a 60-degree radius of transmission, so if we layer them appropriately, it shouldn't be too difficult. And Matt has sort of thought up ways we can essentially encode the signal. Would you like to speak on that a little bit?
Right. Well, the idea is to use either a time division or a code division method for encoding the different signals. The problem that we're running into is So before we can begin to encode the signals and be able to layer them in terms of time or in terms of code, or like Ben said, to get that exact, very precise timestamp using the encoding, we can make sure that the transistors are operating as shortly as possible so we can actually encode without having a pulse time that's like 500 microseconds or something.
And expanding to multiple dimensions compounds that problem because you're receiving more signals.
Some are using two transducers, one transmitter, one receiver,
Right now, yes.
and your minimum distance is,
Our maximum accuracy, minimum distance, well, as
Minimum
they,
distance right now is about 20 millimeters. It gets to the point where you can't, it's about how far we can get it without things hitting each other.
any other questions?
Presentation is the optimal charger for lead acid batteries.
Hello, my name is Gary Woodward. This is Jason Truex and Jose Sierra. Our project is to try to recharge lead acid batteries in an optimal manner so that it's always kept at its full state of charge. Typical use would be either a standby use or a heavy cycle use, so you have to have two ways to charge the lead. If you don't recharge the battery properly, you're going to end up having sulfation in place, and it's going to fail prematurely on you. So we're going to investigate using a pulse charger to try to reverse that. Finally, you have to have some way to figure out if you're doing anything, and we're going to use a constant discharge circuit to measure the capacity of the battery and compare it to the battery manufacturer's original specifications, see if you can gauge any improvements in it. So we started with, Jason did some research on the different types of battery chips that are out there, and we selected the TI DQ2031, which came with the valve board. It was basically selected because it already has 3 modes of operation, and it looked like it would be easy to scale that chip up to a larger voltage and larger power. Jose did the initial research